Hello everyone, welcome to lecture 6 of the online course on Nanophotonics, Plasmonics and Metamaterials. So today's lecture will be on electromagnetic waves in dielectric media. So here is the outline of the lecture. We'll have a quick recap of the wave equation. Then we'll introduce the concept of wave vector k. We'll look into plane waves in dielectric medium, discuss about the concept of wavefront, then constraints due to Maxwell's equations, energy flow, angular frequency, phase velocity, group velocity, dispersion, and finally we'll look into plane waves in lossy dielectric media. So from the last lecture, you must remember that we have discussed how to derive wave equation from Maxwell's equation. So for your quick reference, we have again reproduced the 4 Maxwell's equations here, which can be tabulated in as differential equations and curl equations. Now from the curl equation, we have seen that if we take the curl of this vector, we can introduce curl of b. B you can write as mu h. So curl of h can be replaced by this term, and finally we come up to this vector wave equation. That is del square E equals mu epsilon dot square E dot E square. So it's a second order partial derivative, and this is the vector wave equation. Now this can also be written in this form, like instead of writing E vector using boldface, one can actually write it as this kind of notation. That is also fine, and you can explicitly write that this vector E is a function of position r, that's a vector r vector, and time t. And when you take both the terms on left hand side, you will get this minus. So this is basically the governing equation of the electric field, and this equation is nothing but your wave equation. So you can actually have a look at the electromagnetic wave here, which is propagating along x direction, and you see that the B field, that is the magnetic field, is oscillating along z, and the electric field is oscillating along y direction. And this particular parameter, that is nabla square or del square parameter, is called Laplacian parameter, right? So if you consider Cartesian or rectangular coordinate system, you can write del square as dou square dou x square plus dou square dou y square plus dou square dou z square. So these are all known factors. I'm just quickly giving you an overview. Now let us see that how to write wave equation in frequency domain. Now if you assume a time harmonic wave propagating along x direction, as was shown here, then to obtain the frequency domain wave equation, you have to do Fourier transform, right? So we can use Fourier transform with e to the power I omega t, time dependence. So there should be a t here. So you can write e x of t, because here we assume that the propagation is along x direction. So it is ex e to the power I omega t, and this form is also known as phasor form. So we have introduced one new term here, which is omega, that is nothing but the angular frequency. Now if we take derivative of e to the power I omega t with respect to time, so you can assume t here, you will get I omega e to the power minus I omega t. That means using this you can easily convert the time domain wave equation into frequency domain wave equation by replacing dou t with I omega, and you can replace dou square dou t square using I omega whole square, which comes out to be minus omega square. Okay, so the wave equation can therefore be given as, so you can start with this one, this is your wave equation, okay, and you can finally write that instead of dou square dou t square, you can write I omega whole square, okay, and that will actually give you I square will give you minus 1, that minus gives you plus. So what do you have? You have actually mu epsilon omega square. So if you take velocity of wave v as 1 over square root of mu epsilon, you can write this term as omega over v whole square. Okay, and these terms remain as it is. So you have actually everything in frequency domain now, so you are able to get this kind of equation. So you see that there is a dependence of omega over v, and this particular term we can introduce a new term here, that is called wave number or k. So k can be written as omega over v, or it can be, if you write omega as 2 pi f, where f is the linear frequency, you can write k equals 2 pi f by v. V is the velocity of the wave. So this equation in the form of wave vector or wave number, this is wave number, so you can also call this equation as Helmholtz equation or Helmholtz wave equation. So this is for a particular case where the wave is propagating along x direction. So you can also consider a generic form of this equation, and you can write del square E plus k square E equals 0. So that will be Helmholtz equation in generic form. So we understood wave equation, and then from there we know how to go into the frequency domain and we can obtain the Helmholtz equation. Now let's look into this wave vector concept in more details. So all of the components in general are basically functions of 4 coordinates. So there are basically 3 spatial components, x, y and z. These are the spatial coordinates, and there is also time. So if you actually consider electric field, it is a function of position, as I told you before, and time. So you can write this as E equals cos kxx plus kyy plus kzz minus omega t. This could be a solution to the wave equation. Now here kx, ky and kz are nothing but the x, y and z components of the wave vector k. Okay, omega is the angular frequency. So when you put this form into this particular equation, you will see that you turn up getting kx square plus ky square plus kz square equals omega square mu epsilon. So omega square mu epsilon, you can, this part you can write again as k square. So what do you get here? You actually get to see the same equality that we have seen before. So you can write omega square root of mu epsilon equal k. So 1 by square root of mu epsilon is nothing but v. So that way you can find omega by v is basically k. It's the same thing. So this wave vector k is also known as propagation vector because it tells you the direction of wave propagation. So you can actually write this vector k as I mentioned, kx along x cap, ky along y cap and kz along z cap. So these are the different components along the 3 unit vectors. Now, so we have seen the derivation here that from wave vector or the propagation vector, how we can find out the relationship between omega and k. So if we consider free space, then these values mu and epsilon, they will be mu naught and epsilon naught. That is the permeability and permittivity of the free space. So you can simply write that omega square is basically k square, or if you think about the amplitude only, so you can take modulus of k whole square, that will be divided by these 2 terms. So these 2 comes in the denominator. So for free space they are mu naught and epsilon naught. Okay, and 1 over square root of mu naught epsilon naught is nothing but c. So when you take square root on both sides, you get omega modulus of k times c. Okay, so this relationship is also called the dispersion relation. So omega k relationship is known as dispersion relation. So this tells you the relationship between the wave vector, or modulus of wave vector is nothing but the wave number, okay, wave number and the angular frequency. So here the value is also shown, the magnitude of the wave vector, that is when you take the modulus of this k vector, you can write it as simple k, okay, and that is nothing but 2 pi over lambda. What is lambda? Lambda is the wavelength of light. Here in this case we are considering everything in vacuum, so here it will be wavelength of light in vacuum. If you consider any media, it will be the wavelength of light in that particular medium. Now let us see how plane waves propagate in dielectric media. Okay, so the direction of propagation is actually given by the scalar product of the wave vector k and the position vector r. So that also, so this one basically tells you the direction of propagation. So when you compute k dot r, you get kxx. R is the position vector that can be written as, you know, x cap plus y cap plus z cap. So when you do this dot product, you will get kxx plus kyy plus kzz. So that actually gives you a phase front because k dot r is a constant. So here also you can see k dot r, okay, in both cases you will see that k dot r actually coming along this direction, okay, or you can say these are the constant phase fronts. So phase front is basically nothing but a plane, and the amplitude of the electric field on this plane is a constant. So we can assume the electric field ERT to have this particular form in this case. So that was the solution of our wave equation also. So ERT can be written as E then cos of kxx kyy plus kzz minus omega t. So when all the amplitude are equal, we can consider it as a uniform plane wave. Okay, so first of all, when the phase front is a plane, okay, that's a plane wave, okay, and when the uniform amplitude is there along all the points on this phase front, we call it as a uniform plane wave. Okay, so here is the definition. So uniform plane waves are nothing but waves with constant phase fronts. Okay, so the phase fronts, they are basically planar, and the amplitude E0 is also uniform across this plane. And what is this wavefront? That is nothing but a surface over which the phase of the wave is constant at a given instant, okay, and that is referred to as wavefront. So a wavefront of a plane wave is obviously a infinite plane that is perpendicular to the direction of propagation. And there is also the other case possible, that when the plane wave is non-uniform, it means its phase front is still a plane because it's a plane wave, but the amplitude of the field are not constant. Okay, now since the constant phase front must be perpendicular to the wave vector k all the times, so we can conclude that the phase front also propagates in the same direction as your wave. Okay, so phase front has to travel in the same direction of your k, and at every point on a given plane, okay, is equivalent. So you can also say, like, as far as E and B are concerned, all these points are actually same. So the question comes, how do these wavefronts move as time goes on? So the answer is, these wavefronts must be always perpendicular to the wave vector k, so they will actually have to move in the same direction of k. Okay, I hope that is clear. So now let us see that what are the constraints to this plane wave being put by the Maxwell's equation, because Maxwell's equation tells you about the coupled electric and magnetic fields. So depending on the relationship, there may be some constraints put on the plane waves, so that will be seen here. So now let's see how Maxwell's equation can further constrain the form of the waves. So let's look into the Maxwell's first equation for a source free region. Okay, so here is the Maxwell's first equation when there is no source, that is rho is 0, charge density, surface charge density is 0. So you can simply write del dot E equals 0. Now del dot E can be written as dou Ex okay, dou Ex dx, dou Ey dy plus dou Ez dz, okay, and this partial derivative with respect to space can be converted into ikx. That is how you take their Fouriers, and you can write them in terms of the wave vectors, okay. So this one you can write ikx, this one you can write iky, this one you can write ikz. So from this equation you can also write that this is, you take I common, and because it's 0 on the other side, so it simply becomes kx ex plus ky ey plus kz ez. So this is nothing but the dot product of k vector and e vector. So k and e, the dot product is 0. So when the two vectors have dot product 0, it means they are perpendicular to each other. It means the electric field is basically perpendicular to the direction of wave propagation. And the same thing can also be shown for the second Maxwell's equation, that k dot b is becoming 0, because you will start with del dot b equals 0, and you can do the same exercise and you will write the same conclusion that B, magnetic field, is also perpendicular to the wave propagation. We are saying B also has magnetic field because B is equal mu h, okay. So they can be actually B is particularly, it is basically magnetic flux density, but this also tells you the direction of the magnetic field, okay. Now here let us see the expression of E in the third Maxwell's equation. So this is the third Maxwell's equation, where you have curl of E equals minus dou B dot T. Now curl can be written as, this vector, del vector can be written as dot x comma dot y comma dot z. You are doing a cross product with E, so that actually can be converted into this domain, okay. So this is nothing but ikx. So dot x is nothing but ikx in the Fourier space, okay, and you obtain this one. Time derivatives dot t can be written as minus I omega, okay. So once you see this, you can write this is nothing but your k vector cross E equals omega b. It means the cross product to two vectors is perpendicular to each of them, okay, and that is happen only when B is perpendicular to E. So that means these are the conditions that a plane wave have to follow because of the Maxwell's condition, that electric field will be perpendicular to the propagation direction, magnetic field will be perpendicular to the propagation direction, and electric field and magnetic field will also be orthogonal or perpendicular to each other, okay. So this kind of orientation basically form a right-handed triplet, okay. So you can take this finger along E, this is B, so this will be showing your K direction, wave propagation direction. So it means E cross B, if you do this particular cross product, you will get the same direction as K. It means the wave is finally propagating along the K direction. Now with that, we have to understand when a wave is propagating, there should be some energy associated with it and which direction the energy is flowing. So when electromagnetic wave travels in space, it carries energy, and the energy density is always associated with the electric field and magnetic field. And there is something called Poynting vector, which is named after John Henry Poynting, and this particular vector is used in order to demonstrate the energy flux density of an electromagnetic field. So Poynting vector is nothing but it's a result of the vector product of the fields, electric and magnetic component. So mathematically you can write it as P equals E cross H. Now H can be written as B over mu. So this is how it looks like, E cross B over mu. So Poynting vector again is a vector which is basically cross product of two vectors, so it will be in the direction perpendicular to the plane that is containing E and H. And Poynting vector is also called instantaneous energy flux density, since it represents the rate of energy transfer per unit area. So it has got a unit of watt per meter square. Clear? So the next attribute to the plane wave is the angular frequency. Now, if we have arbitrarily taken a wave that is traveling along, say, positive x direction, then we can write this. So Ey, so you are talking about the electric field component along y direction, x is the propagation direction, and t is the time dependence. So it can be written as E naught cos kx minus omega t. So E naught is the amplitude, and that is, varying as a cosine function. Okay, so if we have chosen its phase so that the maximum field strength occurs at the origin at time t equals 0. So that is why cos function has been taken, that we assume that the maximum field strength is happening when t equals 0. Okay, then at any point of space you can say that the electric field oscillates, okay, at a angular frequency of omega between plus E naught and minus E naught. Let's assume that this maximum amplitude is E naught, and this on the negative side it is minus E naught. So you can say it is oscillating between plus E naught to minus E naught. And what is the frequency? Frequency is omega. Similarly, for magnetic field also, B field also, you can say that it is basically oscillating between plus B naught and minus B naught. Okay, so this is how it has been defined. So the amplitude of the wave is maximum value of Ey xt. So we are writing this electric field as Ey because this is the direction, y direction of the electric field vector, xt because they are propagating along x, okay, and t is the time dependence. So the amplitude of the wave being E naught is basically the maximum amplitude of this particular field. So we also can define the period of oscillation, that is defined as capital T. So that is nothing but the time taken for a complete oscillation from here to here. And once you know capital T, that is the period of oscillation, you can also find out the frequency f. So frequency is nothing but number of complete oscillations, okay, per unit time. So it is basically inverse of this time period t. So from that you can also find out what is the angular frequency omega. So omega equals 2 pi f, and f can be written as 1 over t, so omega can be written as 2 pi over t. Clear? So these are the couple of important concepts. So we have seen wave vector, we have seen the angular frequency. Now let us look into another important attribute of plane wave, which is phase velocity. So the wavelength lambda is a distance covered by one complete cycle of the wave, right? And the wave number k, okay, is basically the number of wavelengths that can fit into a distance of 2 pi. So that is how we have defined this wavelength and wave number. So relationship between k and lambda we have seen, k equals 2 pi upon lambda. So the quantities of electromagnetic wave is basically similar to that of a mechanical wave. So we know omega equals 2 pi f, f is nothing but 1 over t, k is 2 pi by lambda, and c, speed, is nothing but f lambda, which is also written as omega over k. Now if you see this particular relationship, you can also understand that the velocity of the peak of the wave, okay, that is the position of the constant phase, okay. So the velocity requires that omega t minus kx will be constant, okay, here, because the slope is 0, okay. So you can write the velocity of the propagation is then defined as phase velocity. So you can write Vp equals dx over dt, that is omega. From this you can find out that is basically omega by k. Now omega you can write as 2 pi f, and k you can write as 2 pi over lambda, so you get Vp equals f lambda. So that is the phase velocity, okay. Now when an electromagnetic wave is traveling in a dielectric medium, The oscillating electric field basically polarizes the molecule of that medium at a frequency of the wave. And relative permittivity is basically the measure of the ease with which the medium becomes polarized, and hence it also indicates the extent of interaction between that medium and the electromagnetic field. Now if you consider a dielectric medium to have a permittivity of epsilon r and a phase velocity, then you can write the phase velocity Vp will be square root of 1 over epsilon mu. Now epsilon is nothing but epsilon naught times epsilon r, where epsilon r is the relative permittivity, okay, and this is how you can write. So in this case epsilon r also varies with wavelength, okay. So this will be the phase velocity, okay. So phase velocity is also giving you one important thing, that is the ratio of the speed. So once you know this particular phase velocity, you can also find out the ratio of the speed of light in free space, that is given by c, and the speed in a medium, that is its phase velocity, and this ratio is nothing but the refractive index. So that is the definition of refractive index. So n equals c by v or Vp, this is the phase velocity. So you can write square root of epsilon naught epsilon r mu naught divided by epsilon naught mu naught. So you can cancel out the terms and you can write it as square root of epsilon r. So that is how, in a lossless medium, refractive index is same as square root of epsilon r. Now you can also think about dispersion in the sense that that the concept or the notion of phase velocity is defined for plane waves at fixed frequency. Now if the medium is dispersive, that means in dielectrics its permittivity can be dependent on the frequency. In that case, the phase velocity is basically different for waves with different frequency. So if that is the case, how do we deal with it? Because a different frequency will have a different phase velocity, right? So when we deal with propagation of packets of plane wave, that means we are discussing about finite duration pulses, okay, and when you convert it into Fourier spectra of plane waves, you will see that there are different frequency components present. So we need the concept of group velocity to measure what will be the average speed, you can say, of that particular package or the pulse. So the term dispersion refers to the fact that the waves of different frequency travel at different phase velocities, and so the phase velocity Vp and the group velocity Vg, okay, they will not be identical, and it happens whenever the dispersion relationship between omega and k becomes non-linear, okay. So if the relationship is linear, then phase velocity will be same as group velocity. Something like if you take free space, the dispersion relation is omega equals ck. So if you take Vp, that is omega by k, or you take group velocity, that is dou omega by dou k, they will give you the same value c, okay. So in that case they are same. But then if the medium has got a nonlinear dispersion relationship, you will get the two velocities to be different. So if the group velocity is less than phase velocity, that is basically a normal dispersion, and if it is other way, like group velocity is more than the phase velocity, you can call it anomalous dispersion. So let us look into the concept of group velocity in little bit more details. So let us assume in this case that there is a plane wave traveling in z direction, plus z direction, okay, and since there is no perfect monochromatic wave in reality, we have to consider that that a group of waves differing slightly in wavelength is actually traveling. So it is not exactly one particular wavelength, there will be little bit spread in the wavelength, and they are all traveling in the same direction. So you can actually think of in terms of frequency and say that two perfectly harmonic waves with slightly different frequency, one to have omega minus delta omega, another can have frequency of omega plus delta omega, they actually propagate together and they interfere and generate a periodic wave packet which contains an oscillating field at the mean frequency mu, something like this. So they actually create a wave packet where the field inside is basically oscillating at a frequency of omega. Okay, and what we are interested, because it's a group or a packet, we are interested at what speed this packet itself is traveling. And for this packet to determine this velocity, you must focus on the maximum electric field here. So let us look into this again. So if you consider two sinusoidal waves of frequencies will propagate with propagation constant k minus delta k and k plus delta k inside a material, so that the sum will add up like this. So you will have Ex at t can be written as E naught cos omega minus delta omega t minus k minus delta k z. This is one wave. The other wave is E naught cos of omega plus delta omega t minus k plus delta k z. So these are the two waves that we have seen here, and when you do the interference or you add them up together, you can use the trigonometric identity cos A plus cos B, and you can write it in terms of this. So you can finally see that you get 2 E naught cos delta omega t minus delta kz. So that will be one oscillation, and the other one is cos omega t minus kz. So you will see that the sinusoidal wave of frequency omega is amplitude modulated here, okay, by a slowly varying sinusoid which has got a frequency of delta omega, okay. And the system of waves, this one, they will travel along the z direction, which is determined by the speed by the modulating term. So here the modulating term is nothing but cos delta omega t minus delta k z. So in this case, the maximum in the field will occur. So this is the maximum. So maximum in the field will occur when delta omega t minus delta kz will be constant, that is basically 2 pi m. What is m? M is integer, okay. In that case, you can find out what is the velocity. So delta z by delta t, or dou z by dou t, if you do, you will come up with dou omega by dou k. So this is the definition of the group velocity. So Vg, group velocity, should be written as dou omega by dou k. So this is kind of a derivation of how to we come to this particular relationship of the group velocity. Now the group velocity represents the speed with which the energy of the information is propagating, since it defines the speed of the envelope of the amplitude variation. The maximum electric field in the figure advances, that is Emax, that advances with a velocity of Vg, and whereas the phase variation in the electric field, so these are the phase variation in the electric field, they actually propagate with a phase velocity of Vp. So once again, the amplitude, the maximum amplitude, that is the electric field amplitude, that propagates with Vg, that propagates through this envelope, and the phase variations, they do this first oscillation and they have this phase velocity of Vp, okay. So in vacuum, we know the dispersion relation is omega equals Ck. So in vacuum, the group velocity is also d omega by dk. If you do, you will get C, that is same as phase velocity. So as I mentioned, in vacuum or air, group velocity is same as phase velocity. So this we have already seen, that the maximum electric field in that figure advances with the group velocity of Vg, whereas the phase variations in the electric field, that propagated with phase velocity of Vp. Now for an electromagnetic wave in a medium, k is the propagation constant inside the medium. So it can be written as k equals 2 pi n over lambda naught. What is n? N is the refractive index of that medium, and lambda naught is the free space wavelength. There is a typo here, is space, okay. So the group velocity then is not necessarily the same as the phase velocity Vp, omega by k, and is given by C by n, okay. So the group velocity definition, Vg equals dou omega by dou k, depends on how the propagation changes in the medium, dk or dou k, okay. That is how the propagation constant changes in the medium with the change in the frequency, that is dou omega. That is why this ratio is important for finding out the phase velocity. And it is not necessarily same as omega over k when the refractive index has a wavelength dependence. So if you get n is different for different wavelength, so there are material which are dispersive in nature. That means the refractive index is not same throughout. At different wavelengths they have a slightly different refractive index. For those kind of material also, group velocity and phase velocity will not remain same. Okay, so that brings a new concept here, that is called group index. So if you consider the refractive index of the dielectric medium, n is basically a function of the wavelength. So n is basically n lambda naught, that is the refractive index is a function of free space wavelength lambda naught. Okay, so in that case you can consider omega equals 2 pi c over lambda naught. Okay, and k is nothing but 2 pi n over lambda naught. Okay, so k is basically the wave vector inside that particular dielectric medium of refractive index n. Okay, now we can find out the group velocity, but by first finding you need dou omega and dou k. So this one, so you take this equation omega equals 2 pi c by lambda naught, and to get dou omega you differentiate it. Okay, so that gives you minus 2 pi c over lambda naught square dou lambda naught. Fine, and then you take k equals 2 pi n over lambda naught, and there also you can do the differentiation. You can write dou k equals, okay, so this is how you differentiate it. So here this is also a function of lambda naught, so that is why you have to do it in two parts, and finally you can add up together. I am just not reading out these terms, you can simply see this is a very simple calculation. And finally you can write Vg equals dou omega by dou k. So dou omega you can bring this term, and dou k you can bring this term, and then when you make the common terms cancel out each other, you will be left out with c over n minus lambda naught dou n over dou lambda naught, that is lambda naught, that is the free space wavelength, times the derivative, the way the refractive index is changing with lambda naught. So that term comes into picture. So that is how you can write Vg is nothing but c over Ng, capital Ng, that is the group index. Okay, so group index belongs to a plane wave of certain frequencies, okay, traveling inside a particular dispersive media. Okay, so you can write also what is Ng, that is the group index of this medium. So this particular medium n has got a dependence of lambda. For that you can find out what is the group index of that medium, and it can be given as n minus lambda naught dn over d lambda naught. Okay, so now let's look into the dispersion. So in general, for many materials the refractive index n and hence the group index Ng that depend on the wavelength of light by virtue of epsilon r being frequency dependent. Okay, so in those cases the group velocity and the phase velocity and the group velocity both depend on wavelength, and these are the kind of medium which is called dispersive medium, where both phase velocity and group velocity is dependent on wavelength. Now if you consider a light traveling in a pure silica glass medium, and if the wavelength of light is 1 micron and the refractive index at that wavelength is 1.450 micron, then what will be the phase velocity, group index and group velocity? Okay, so you can actually look into the dispersion curve of silica given here. So here is the refractive index, how it is varying with wavelength, and also how the group index is varying with wavelength. So you can find phase velocity using this formula, V equals C by N. That's very simple. So V equals C by N, C you already know, N at 1 micron is already given, 1.450. You put it, you get this value. So that is the speed, phase velocity. Now what is group index? At lambda equal 1, so lambda equal 1 is this one. So here you can see your Ng is 1.463. So once you know Ng, that is your group index, you can find out group velocity Vg, that is C over Ng. C you already know, you put the value of Ng, you can find out what is the group velocity. So here if you compare these two, you will see that the group velocity is roughly 0.9 times smaller than the phase velocity, and that is usually the case. So this is the case of normal dispersion, right? Now till now we have considered like the plane wave propagation in either free space or perfect dielectric, that is lossless dielectric. But in this case dielectric we have essentially used it as a synonym for insulator. So we have been studying plane wave propagation through perfect insulators, but in reality there is no such thing called perfect insulator. So what effect will the conductivity of the material bring into the picture? That means if the dielectric is basically lossy. Now a lossy dielectric can be described as a medium where some fraction of the electromagnetic field power is basically lost when the wave is propagating. So that is how it is lossy. Now this power loss is basically due to poor conduction. A lossy dielectric offers a partially conducting medium with a non-zero conductivity. So sigma becomes non-zero. The lossy dielectric can be represented by its conductivity, permeability and permittivity using this kind of values. So you can denote a lossy dielectric as sigma not equals 0, and then epsilon equals epsilon r, epsilon naught, mu is nothing but mu r and mu naught. So once you do that, you will have some changes in the wave equation. So the wave equation for electromagnetic propagation in lossless media we have seen, this was the value del square E plus omega naught omega square mu epsilon E equals 0, right? You could have written this part as k square and we would have called this as Helmholtz equation. So that is all fine. Now if you consider that for lossy medium J is nothing but sigma E. So if you go back to Maxwell's fourth equation and you write curl of H, then becomes J, that is sigma E, plus dou D dot E. So D can be written as epsilon E and dou dot T can be written as J omega. Okay, so that way you can write, you take E common, you can write sigma plus J omega epsilon. Okay, so in the other cases we have seen sigma was 0 in the lossless case. Okay, but here you are actually having a finite value of, this is a non-zero. Okay, so let us denote this term as a complex permittivity. So you are writing as epsilon C. So it's nothing but J omega epsilon C E. So you can actually define this new constant epsilon C can be written as epsilon minus J omega sigma over omega. So once you do that, you can put it back in the form of Helmholtz equation, and this time the Helmholtz equation changes. So only change will be del square E plus omega square mu. This, instead of this epsilon you will have this epsilon C. Okay, and this term can also be written as minus gamma square E. So let us see what is this gamma. So this gamma is nothing but the propagation constant and it is defined as JKC. So Kc can be written as omega square root of omega by n. Okay, or instead of that you can write omega square root of mu epsilon C, and gamma can also be written in two parts like alpha plus j beta, where alpha is basically the attenuation constant and beta is basically the phase constant or the propagation constant. Okay, so you can equate the real part to the real part and imaginary part to the imaginary part and find out what are this. So you can briefly say gamma is nothing but alpha plus j beta. So alpha is nothing but the attenuation constant, which is a measure of the spatial rate of decay of the electromagnetic wave in the medium. Okay, that means the rate at which it is getting decayed. So it can be written in terms of Nepers per meter, or you can also write in decibel per meter. Phase constant is basically a measure of the phase shift per length, or you can also call it as phase constant or wave number. So that we have already seen. So once you understand these two property, in terms of mu, epsilon and sigma, you can represent alpha and beta in this particular form. Okay, so they are very identical equation, only this is minus and this is plus. Okay, and what you have seen, that from this you can also obtain what is the intrinsic impedance of the medium, that is eta, that is given by square root of j omega mu over sigma plus j omega epsilon. Now in the case of free space where conductivity is 0, okay, this turns out to be, this term goes out, j omega goes out, you simply have omega, and this is mu naught over epsilon naught, and eta naught, that is the free space intrinsic impedance, will be nothing but square root of mu naught over epsilon naught. That is a standard value, everybody knows it's 120 pi or 377 ohm. Okay, so if you consider the material to have a permittivity, so if the material is absorbing, we can say the material also has a complex permittivity. Okay, similarly in terms of refractive index, you can say that the material, any absorbing material, has got a complex refractive index n. So n now will have two parts, that is real part and imaginary part, so n prime and n double prime. Okay, and this is how they can be correlated. So you can write what is k. K is plus minus omega n over c, and n can be written as n prime plus I n double prime, and then you can split them out in real and imaginary part, and then equate this with beta minus I alpha by 2. Okay, so that way you can also find out. So if you only investigate the wave vector or wave number with positive sign, okay, in that case you can write down the wave equation or the electric field expression like this. So EZT, okay, will have real Ez omega exponential minus I beta z, so that tells you about the travelling wave, minus alpha by 2 over z. So this terms tells you the decay constant with z. Okay, so I think this is z. So and this is, anyways, this is correct, because if the propagation direction is x, the decay term here is also correct. It is nothing but exponential. Okay, you can see this term beta is nothing but kn prime. So a decay term is basically this one. Okay, it is beta and alpha. So beta is the travelling wave term. So beta is omega over c n prime, that is kn prime. Alpha is minus 2 omega by c n double prime. So that is nothing but minus 2 k n double prime. So from here you can also see this is alpha by 2, so 2 cancels out, it is only minus k naught n double prime and x. X is nothing but the propagation direction, here we have considered x propagation direction, though here we have taken the equation along z. If it is along x, you make it to x, this will be x and this will also be x. Okay, so that is fine. So what I mean to say that here the wave will be propagating, but then along with the propagation the amplitude will not remain same, it will keep on decaying, and this will be the rate of decay. Okay, so with that we'll stop here, and in the next lecture we'll discuss about polarization optics. And in case you have any query on this particular topic and any questions, you can drop an email to this email address. Thank you.